bit excited, so I might be a little bit nervous during presentation. I'm Ehsan Nikkhah. I'm the PRH7 doctorate student of Ocean and Naval Engineering Department. My advisor is Professor Antonio Fernandez. My thesis title is Artificial Neural Network and Prospective Methods Applied to FPSO Mooring Line Design, including the mooring line damping effect. And station keeping of an FPSO in an offshore site will provide by mooring lines against wave, wind, and current. As can be seen here, this chopper operation can be done safely against strong wind, which the flare burning to the left side, and a strong current. The presence of mooring lines will introduce additional damping on the system. The main damping contribution from mooring lines is due to hydrodynamic drag, while the FPSO moving transversely or longitudinally. The larger depth will increase the mooring line damping effect due to larger suspended length of the mooring lines. As can be seen here, this is the FPSO 3-decade curve of surge motion for two different mooring depths. As can be seen, the large depth mooring has higher damping effect than medium depth mooring. Two major profiles are going to be used for mooring line of an FPSO. The catenary anchor mooring and the turtleneck mooring. The catenary anchor mooring taking advantage of geometric stiffness in order to provide restoring force, while the turtleneck mooring use elastic stiffness to provide restoring force. Catenary anchor mooring mostly used for shallow waters and due to heaviness of the chain material is the dominant choice, while the turtleneck mooring mostly used for deep waters and because of the lightness of polyester is the dominant choice. At the anchor point of catenary anchor mooring, only we have horizontal force, so drag-embedded anchor is required, while for the turtleneck mooring, the deep penetrated anchor is needed because both horizontal and vertical force must be tolerated at the anchor point. Regarding the same length for both profile, the catenary anchor mooring has much higher damping effect than turtleneck mooring. Considering the choice of material for mooring lines, a mooring line in deep water is multi-segment and usually made up of more than one material. The benefit of segmentating gives greater stiffness while giving the lighter anchor lines. It usually has the chain, steel cable chain, or chain synthetic rope chain structure. Synthetic ropes are much lighter. They have very high strength to weight ratio, better absorb dynamic motion through a slight elongation, have higher endurance fatigue, and excellent vibration damping than a steel cable. The most common synthetic rope materials are polypropylene nylon, polyester, and aramid chain PE. Polyester is more economical and better choice for fatigue resistance, abrasion, and elasticity. A very nice industrial application of mooring line damping is mooring line reduction. As can be seen here, this is the 3-decade test results of surge motion for three different mooring arrangements. The same floater, but the mooring system just varies in number of mooring lines. The characteristics and properties of mooring lines are the same. As can be seen, 24 mooring lines shows higher damping effect than 12 mooring lines. It's a great idea to harness the same floater with lower number of mooring lines while having the damping effect of larger number of mooring lines. This is the purpose of this study that we are going to design and analyze a floater with lower number of mooring lines. In order to study the mooring line damping effect, having a simplified dynamic model of a mooring line is necessary. This simplified dynamic model is the same as the mass spring damper, but with a little bit variation. For mass, we have submerged mass of the mooring line plus added mass. For damping, we have drag force, which is the viscous damping. For stiffness, we have the elastic stiffness, and the applied load here is the dynamic tension through the mooring lines. Mooring lines can be divided into different number of elements. Each of these elements can be treated as a mass spring damper. This method is called lumping mass method. This method is nowadays used for most mooring analysis software such as Orcaflex and so on. In order to analyze the mooring line in a dynamic mood, first we have to analyze it in a static situation. For a static situation, we have the standard catenary equation for mooring lines. We can divide the mooring lines into a number of elements and nodes. Each element can be lumped into one lumped mass, which have both characteristics and weights of both elements at the same time. With discretizing the catenary equation of mooring lines and taking advantage of MATLAB software, we can make a very nice static model of the mooring line. For the dynamic model, after the static analysis, because this static mooring line is going to be used as the initial condition of the dynamic model. The mass, damping, and stiffness matrix can be found by approximating each element as a rod moving, because we are going to use the finite element method. The mass and stiffness matrix for the rod elements, considering just 4 degrees of freedom. We have only the 2 nodes out of each element. Each node have the 2 degrees of freedom. One is direction to the x, one is to the y. The mass and stiffness matrix can be found by these two equations. Submerged mass of each element, the added mass of each element can be found by these 2 equations. For the viscous damping, on the other hand, also we can use these equation. I found this from the paper from the Bergen. I studied mooring line damping from Norway. Each of these added mass coefficients and drag coefficient for different materials of each rod can be found in a DMV-GL standard. The added mass coefficient for chain is 3, for polyester is 2. The drag coefficient for chain and polyester is 2.4 and 1.8 respectively. Considering this method, first we did the static mooring line analysis. These 4 functions in the MATLAB can be used, which static mooring computes the multi-segment line static mooring model and the initial condition for the dynamic model. The dynamic mooring initiates the dynamic mooring model. The dynamic mooring step solves one step of the dynamic mooring model. And the dynamic mooring iterates the dynamic mooring model through I to n steps. This is the case study of as a sample in order to see what's going on in this MATLAB code. The length of chain, which is the lower segment, is 450 meters. The length of polyester made 1500 meters. The length of fairly chain is 100 meters. The submerged weight of chain is 93.6. Submerged weight of polyester is 16.8. The modular of elasticity for chain and polyester is 211 and 5 gigapascal. And these are the nominal diameter of chain and polyester, and we did this analysis in 1400 meter water depth. This is the results coming from the static analysis. I choose different submerged weight for chain to see the difference of the geometric stiffness for different profile while having the same tension at the ferry. As can be seen, the much higher weights will give much higher catenary shape and much steeper angle at the ferry. Another time, we made the same. I made the same submerged weight for the chain, but this time changed the tension at the ferry. As can be seen, the much higher tension at the ferry will have the much higher suspended length of the catenary chain. For the dynamic analysis, a step load, a load size of 700 kilonewtons. This is the step force for the dynamic analysis. At the period of 60 seconds applied for the mooring line to see the dynamic behavior of the mooring line. As can be seen, these dotted lines are the profile of the mooring line after 60 seconds while having the 700 step force. This is the end node displacement. This end node displacement after 60 seconds. Each second divided to 0.02 steps. 60 seconds divided to 3000 steps. As can be seen, at the within the first short of applying this load, we have a very high displacement, but very quickly getting damped. For the displacement of end node, and also for the y displacement of end node. Out of these predefined damping matrix and stiffness matrix, these are the damping coefficients found for different elements of mooring lines, which summation of these damping coefficients are the mooring line damping effect, which is the drag force of mooring line while moving through these 60 seconds. This is the time schedule I've made for this analysis from November 2021 to April 2022. Fortunately, with new regulation of FINEP, I'm going to my obligatory courses this semester. This semester I have only this course, the mathematics for Engenharia 1. I already succeeded to pass these green courses. Herewith, I will appreciate the ANP and PRH for the financial support. Thank you very much.
If you have some questions to answer, some comments, Professor Tatali.
Yeah.
So thank you very much.